We can draw two free body diagrams to help us solve this problem, illustrating the forces on the hoop, radius big R, mass big M, and the forces on the beads, mass little m, at position θ from the vertical around the ring. Denote the radial normal force that the beads exert on the ring as R1 and R2, and the radial normal force that the ring exerts on each bead as R1' and R2' respectively. Remember to include big N, the normal reaction force from the ground acting on the hoop. Due to the symmetry of the setup, R1 and R2 must always have the same magnitude at the same point in time, and according to Newton, R1 and R1' must be equal and opposite, and the same for the second bead. As the beads are moving in a circular path around the hoop, there must be a centripetal force acting on them, provided by a radial force. This radial force can be found by finding the radial components of the weight of each bead and R1' or R2' respectively, while the centripetal force, which we know this must be equal to, can be expressed in terms of V1 or V2, the velocity of the bead in question. Again, due to symmetry, V1 and V2 must have the same magnitude. As the speed of the beads is constantly changing as they move around the hoop, the centripetal force is also not a constant. As the beads move around the hoop, energy must be conserved. This allows us to find little v. You may find it useful choosing the top of the hoop as the point of zero potential energy, so when θ equals 0, in which case the initial energy of the system must be 0. We can then express the total energy of each bead at any point in terms of its kinetic energy and its gravitational potential energy, where the change in height can be written in terms of θ, giving us an equation relating v to θ as in velocity to position. We can now substitute the expression we have just found for v, the velocity, back into our equation relating the radial forces to circular motion. Remembering that R1 and R1' and R2 and R2' have the same magnitude, we can now find the condition for the hoop to rise by resolving forces vertically and considering what must happen to big N as the hoop is lifted off the ground.